In section 5.3, we are looking at expressions of the form a cos x plus or minus b sine x. A and b here are constants. They could be positive, they could be negative. It is possible to write expressions of this form, where a and b are constants, as a sine function only or a cosine function only. And that's the key to this little section. Converting something that is the sum of two terms, one in cos and one in sine, and converting it into a single sine function or a single cosine function. Now, if you sketch or draw on your calculator or on a graphing package such as Desmos, the graph of 3 sine x plus 4 cos x, and this is what you'll get on the right hand side, I've done it on Desmos, you will see that it has the form of a sine graph or a cos graph. It's got that familiar shape, but it's been stretched. The sine and cos graphs only go up to 1 on the y-axis and down to -1. This one's gone up to 5, down to -5. So it's been stretched vertically and also been translated horizontally as well. The sine graph goes through the origin, the cosine graph goes through the y-axis at a maximum point. This one does neither, so it's definitely been moved horizontally. We're going to learn how to use the addition formulae and convert all expressions of this form into one of the following forms, either capital R times sine of x plus or minus alpha, where we choose R to be positive. We could choose it to be negative, but it's easier if we choose it to be positive, and alpha is an acute angle. Alternatively, we could go for capital R multiplied by cos of x plus or minus beta. Again, we choose R to be positive, and beta is an acute angle. So just remember, the graph of y equals a multiplied by f of x take away 8 is just the graph of f of x stretched vertically by a scale factor of a and translated horizontally by b. That's a reminder or revision from graph transformations. So here we go, our first example of converting an expression of the form a cos x plus or minus b sine x into a single sine or cos function. Our example is the one we graphed on the previous slide, 3 sine x plus 4 cos x. We're going to write it in this form, r multiplied by sine of x plus alpha, where r is positive and alpha is an acute angle. Give your values of r and alpha to one decimal place where appropriate. So if we can write them exactly, then we do. If we can't, we give them to one decimal place. Well, the first thing we're going to do is use the addition formulae and expand r sine x plus alpha. Up at the top of the screen, I've written out what you get in the formula book. Sine of a plus b is sine a cos b plus cos a sine b. Let's use that now and expand r sine x plus alpha, which was the form given to us in the question. That's how we want to express 3 sine x plus 4 cos x. So have a go now, expand that using the addition formula. So I hope you got this. R sine x cos alpha plus another r cos x sine alpha. Whatever you do, don't forget this r. Now you might have written it with brackets. You might have written r and then open brackets sine x plus cos alpha plus cos x sine alpha, close brackets. Of course, that's the same thing. But we're going to need to expand those brackets. So the quickest thing to do is to go straight for this version with no brackets. Very important step coming up now. I'm going to compare what I've just written down with the expression that we are working with in this question. I'm going to compare them. So first of all, let's look at the sine x term. So this is the sine x term here. Now we want these two expressions to be the same. We want this that we started with. We want it to be the same as this, because if it is, then that means we can write it in the form r sine x plus alpha, which is what we are trying to do. But at the moment we're looking at these and trying to make these the same. So I've underlined sine x where it appears. We can now write down an equation from that. If I look at those two expressions, I can say 3 must be the same as r cos alpha. That comes from comparing these. If these two terms really are the same, then the number 3 there must be the same as r times cos alpha here. Then in each case we'll have 3 sine x. We'll have the same number, and that's really important. So there's equation number 1. Let's go and get another equation by looking at the cos x. So try and think before I write it down, what equation will we get this time? Compare these. These need to be the same. So therefore, what can we write down? Well, we can write down that 4 must be the same as r sine alpha. Very important that you get these two equations correct, because obviously if these two equations are wrong, we're never going to get the right value of r or the right value of alpha. I'm going to number these equation 1 and equation 2, and let's go ahead and find the value of r and the value of alpha. Now the way I'm going to find r, first time you see this, it might seem quite long-winded, but actually it's the best way to do it. I'm going to square the two equations and add them together. Square the two equations and add them together. Let's do on the left-hand sides. So on the left-hand side, 3 squared plus 4 squared. I'm squaring each equation and then adding them together. So I've done the left-hand sides first. Let's do the right-hand sides now. Square the right-hand side and add them together. This might look complicated, but actually on the right-hand side, if we take out a common factor of r squared, then I hope you recognize an identity. We've got cos squared of an angle plus sine squared of the same angle, and that always equals 1. So this right-hand side is just r squared. And that's one of the reasons why this is a good method, because next time you do a question like this, you can maybe go straight to just r squared. You don't need to show all of this every time. You could just go straight to r squared. On the left-hand side, we've got 3 squared plus 4 squared, which is 5 squared, which is 25. So if r squared is 25, we could choose r to be positive 5 or negative 5. It makes things simpler if we choose it to be positive, and the question tells us choose a positive value of r. So r is 5. Now that we've got r, we can work out alpha. Now you could substitute our r value back into either one of these original two equations. I recommend doing it a different way, just in case this value of r is wrong. So here's what I would recommend, an alternative. If we do equation 2 divided by equation 1, so do the left-hand side first, 4 divided by 3. And now the right-hand side is r sine alpha over r cos alpha. Notice we've got r divided by r, which is 1, so the r's cancel each other. And that's why this is a good method, because if r was wrong, then it's not going to matter. Now there's a reason I did equation 2 divided by equation 1 and not the other way around, because I looked at them and I knew I could get sine over cos, which is tan. If I did it the other way around, I'd get cot, which would just give me an extra step of rearranging to do. Not a massive problem, but it makes sense to do it as efficiently as possible. So sine alpha over cos alpha is tan alpha. Now we can do inverse tan of 4/3. So inverse tan or arctan means the same thing, of 4/3 is alpha. Take a look at the question. Are we in degrees or radians? Hopefully by now you've trained yourself to always check and get the calculator in the correct mode. I've got 53.1 degrees on the calculator. Now we can't write that exactly, so this is a case of 1 decimal place like the question told us to do. So we've got r, we've got alpha. All that remains is to answer the question. Show that we can express 3 sine x plus 4 cos x in the form r sine x plus alpha. So therefore, we've found that 3 sine x plus 4 cos x is exactly the same as, and I'm going back to my first line now. It's exactly the same as, well, we've got an r value of 5 and an alpha value of 53.1. So it's 5 sine of x plus 53.1 degrees. And that last bit there is the answer to the question. Everything else was working out. Now, if you think back to the previous slide, we drew the graph of 3 sine x plus 4 cos x, and we noticed it had been stretched vertically. We noticed it went up to 5 on the y-axis and down to -5. Well, there we have the stretch, scale factor 5. That would do that job. And we also noticed it had been translated horizontally. And now we know how much it was translated horizontally. There we go, first example. You might not fully understand the method straight away, but that was our first example. It might take a few goes and maybe a little bit of time before you feel completely confident with this method. Let's crack on now with another example. So going on to example 5.3.2. Example 5.3.2, we're going to show that we can express sine x take away root 3 cos x in the form r sine x take away alpha. This time note straight away alpha is in radians, so get your calculator into radians mode. Just like in the previous example, I'm going to start by expanding r sine of x take away alpha. That's what the question has specified. If it doesn't specify what form to write it in, then we're free to choose. But for now, it's given us that form, so we've got to use it. So let's go ahead and expand that. Hopefully you got this, r sine x cos alpha, take away r cos x sine alpha. If you wrote the r in front of a pair of brackets, then expand those brackets because we need to get rid of them. Next, start comparing sine x terms and compare the cos x terms, and then write down two equations. Have a go at writing down those equations now, so pause the video and have a go. Hopefully these are the two equations that you got. Note that we have a minus in front of the cos x term in both cases. So I could have put minus root 3 equals minus r sine alpha, but then I'd just be able to simplify that equation by times both sides by -1 to get rid of the minuses. So there's no point including them. We've got the right structure. We've got the minus that we need. So root 3 must be the same as r sine alpha. You don't have to label them 1 and 2, but I always do. So now try and remember how we did the first example and go ahead and find r and alpha. I'm going to pause for a few seconds. I suggest you pause the video and work out r, work out alpha. Right, first of all I've got r. Simplest way to square both equations and add them together. Now you saw in the previous example how the right hand side simplified down to just r squared. So when you're working out, it's okay just to put r squared. Unless the question told you you really need to show absolutely every step, you'd be okay going straight to r squared. And on the left hand side, 1 squared plus the square root of 3 squared, so 1 plus 3, which is 4. So very quickly we get r is 2. I'm now going to go and find alpha. There we go, I've divided the equations such that I get tan alpha. So I look for the one that has sine in, which won't always be labelled as equation number 2, just so happened to be equation number 2 again in this equation, sorry, in this example. So did the sine equation divided by the cosine equation, r's cancel, leaves me with tan, and then inverse tan of root 3. Remembering we're in radians is exactly pi over 3. So for part A, we can now say that sine x take away root 3 cos x is exactly the same as 2, because that's the value of r, so 2 sine x take away pi over 3. So they are exactly the same for all values of x. Right, in part B, and this is quite a common follow-up to a task like part A, you're now being asked to sketch the graph. Well, this is one of the advantages of converting it into the form r sine x minus alpha, because if we were just given the original expression, that's really hard to sketch. But in this new version that we found from part A, we can now sketch this graph. So it's the sine graph, but it has been stretched by a scale factor of 2 in the y direction, and it's been translated horizontally by pi over 3. Something the question should have said is for what range of x values to draw the graph for. Let's just go for 0 to 2 pi. So let's go x between 0 and 2 pi. So I've done a it's a terrible sketch of the basic sine graph, but I'm just going to use that as a reference point. I'm going to get rid of it in a moment. So that needs stretching by a scale factor of 2 in the y direction, and then translating to the right by pi over 3. So if we go, here's my attempt. I'm just going to get rid of the original sine graph that I used as a reference point. So this is one full period of our graph. Please make sure it starts and finishes at roughly the same y value. So your graph looks like it's starting and finishing at about the same y value. If it's definitely not starting at the same y value, you possibly would lose a mark for accuracy on your sketch. So the sine graph used to go through the origin. It's moved to the right by pi over 3. So you could even say on the horizontal axis, this is pi over 3. Which in this case, if you then add pi onto that, this is going to be 4 pi over 3 here. And there we go, that is a sketch. Oh, let's just put on the maximum y value 2 and the minimum y value of minus 2 as well. So there's a sketch of the graph of y equals sine x take away root 3 cos x. Third and final example in this section, have a go before you see my solution of doing part A. Write it in the form r cos theta take away alpha. Note that if the question hadn't told us to write it in this form, we'd be free to choose whatever form we want to. And there are 4 options, either r sine theta plus alpha, or r sine theta take away alpha, or r cos theta plus alpha, or r sine theta minus alpha. So there's always 4 options if the question hasn't told you which one to use. However, only 2 of them would be sensible. Looking at the format of the expression, both terms are positive. Both terms are positive. So if we go back to the 4 options, only r sine theta plus alpha and r cos theta take away alpha would be the sensible ones to use, because these are the ones that give us 2 positive terms. But that's if the question allowed you to choose whatever form you want. Of course, this one has specified, so please have a go now, pause the video and get this in the form r cos theta minus alpha. Step 1, expand. Note we'll have a plus in the middle here. R cos theta minus alpha has a plus in the middle, and we've got an r with both terms as well. Here are the 2 equations. 2 equals r cos alpha and 5 equals r sine alpha. Now go ahead and find r and alpha. And there we go. I got r was the square root of 29. Alpha, which needed to be in degrees, 68.2 degrees. The question didn't say 1 decimal place, but that's what I've gone for. Or you could say 3 significant figures. Note we rarely, if ever, round r. If r isn't an integer, then at least we can write it as a surd, which is always better than rounding it. So we generally keep r exact. So this is what we've got. Now we're going to use that in part B. B starts with the word hence, so there's a clue to use what you've just done. Solve the equation 2 cos theta plus 5 sin theta equals 3. Notice that is exactly the same expression that we've just manipulated. So if you were given this equation in part B, then you'd have to use this method, the R alpha method that we've been learning in section 5.3, to rewrite it as a single sine or single cosine function to be able to solve the equation. So what I've done there is replace the left-hand side of the equation in part B with what we found it to be the same as from part A. although I've written 68.2 on my calculator, I've still got the unrounded version of that. I've stored it in the calculator's memory. I'm going to need it in part B. So this is just a case of rearranging now to get cos on its own. So dividing both sides by root 29. Once we've done that, we need to do a little substitution. I'm going to let x, because we haven't used x in this question, equal the angle. So if the question says theta between 0 and 360, then x, which is theta take away 68.2, is going to be between minus 68.2 and 291.8. Again, they're rounded, but I'm storing the unrounded version on my calculator. So now for part B, I'm going to solve cos x equals 3 over root 29 and get values for x between minus 68.2 and 291.8. A quick sketch of the cos graph, and I need to include some of the negative x-axis here. So I've gone all the way up to 360 and back to 90. So there's 90, there's 180, there's 270. Now I'm going to do inverse cos of 3 over root 29. I get 56.1. So 3 over root 29 is a positive number. And I can see from my graph 56.1, which is on the calculator, will be about there. So we're also going to have from symmetry negative 56.1 as well, which fits inside this interval. So I'm going to include that. Let's look at the other end. This one here. That's going to be 360 minus 56.1. Let's go further down. 360 minus 56.1. Which is 303, which is too big. It's bigger than 291, so that's not going to fall in the range theta from 0 to 360, so we don't want to include that one, or we don't need to. It's going to be outside the range. So I've got x values of plus or minus 56.1. I'm just going to write a few more decimal places. 145. ... That's from the calculator, doing inverse cos of 3 over root 29. And since theta is going to be x plus 68.2, then theta is going to be the 68.2 that I stored on the calculator, and then plus 56.1, or take away 56.1. Both of those are going to give us answers. And there we have 12.1 degrees and 124 degrees. I've rounded those to 3 significant figures. If the question told you to use 1 decimal place, then of course you'd have to use that. There we go. That concludes the little section on the R alpha method, converting expressions of the form a cos x plus b sin x into a single sine function or a single cosine function. This skill might need a lot of practice. It often does. So now is a good time to go and practice that.